This is the warm-up for lesson 27. A community pool is being drained for cleaning. At 9 a.m. the pool is 12 feet deep. At 1 p.m. the pool is 10 feet deep. What is the average rate of change of the water level in feet per hour? So average rate of change, that just means what's the slope? Slope is change in y over change in x. And so we need our 2 points. At 9 a.m. the pool is 12 feet deep, so that's a point. 9, 12. And at 1 p.m. the pool is 10 feet deep. Now the problem with time is that a clock goes to 12 o'clock and then it goes back to 1. So 1 p.m. as according to time we'd say is 13. So at 13 we're at 10 feet deep. Our change in y from 12 to get to 10, we're going down 2. From 9 to go to 13, we're going up 4. So this can be simplified to down 1 over 2, and it wants it in feet per hour, so I need to get my change in x. My x is my time, 9 o'clock and 13 or 1 o'clock. So I need this over 1. So this is 1/2, so it's just negative 1/2, meaning we're going down 1/2 foot per hour. Our next problem, you are the pilot of an airliner flying at 30,000 feet. It's 1 p.m. Your scheduled arrival time at Chicago O'Hare is 1:45. Your optimum rate of descent is 1,000 feet per minute. What time will you start your descent to arrive on time? So we're up here in a plane. Okay. And we're 30,000 feet high. 30,000 feet. And it's 1 o'clock. 1 p.m. And we want to land down here in Chicago, in the Windy City, at 1:45. So we want to land at 1:45. And it says our rate of descent is 1,000 feet per minute. So how long, if we're going down at 1,000 feet per minute, how long will it take us to go down 30,000 feet? Well, that's 30 minutes. So the question is, what time should we start our descent to arrive on time? Well, if I wanted to arrive at 1:45 and it takes me 30 minutes, then I'm just going to say 1:45 minus 30 minutes, and we need to start our descent at 1:15. So in 15 minutes, we need to start going down. Homework questions we'll do in class. And today we're going over parallel and perpendicular lines. We're going to be able to tell whether or not we're dealing with parallel and perpendicular lines, and how specifically how we can tell that two lines are perpendicular or how two lines are parallel. So let's graph these two equations. I can graph this first equation by doing the x and y intercepts. So the x-intercept all along our x-axis, remember that our y values are 0, so if I plug in a 0 for y, I can find my x-intercept. That gets rid of my whole y term, so I'm just left with negative 3x equals negative 6. We can divide by negative 3, and we get x equals 2. So our x-intercept is at 2. Our y-intercept, same thing, only now we're on our y-axis, so all our x values are 0. So negative 3 times 0 plus 2y equals negative 6. That gets rid of the whole x term. Divide by 2, and we say our y-intercept is negative 3. So it looks like we're going up 3 and over 2, up 3 and over 2, up 3 and over 2. We can move down 3, and left 2, and we've got a line. Now we can take the information from this line and we can write a new equation in slope-intercept form. So we can look and see that our y-intercept is at -3. Our y-intercept is a b value, so our b value is -3. B is -3. And our slope, we're going up 3 over 2, so our slope is up 3 over 2. And so we can write our equation, y equals 3/2 x, and our y-intercept is -3, so 3/2 x minus 3. So that's that new equation. Let's graph this other equation. Looks like our y-intercept is at 4. And our slope is 3/2, so we're going to go up 3 and over 2. If we're moving the other direction, we go down 3 and left 2, down 3 and left 2, down 3 and left 2. And we've got our lines. So what do these lines look like? These lines look like parallel lines. What do we notice about their equations? We should notice that my first line had a slope of 3/2 and our second line had a slope of 3/2. And that's how we prove that lines are parallel. Not only do they look like they're going to never touch, but that they have the same slope. They'll also have different y-intercepts. If they had the same y-intercept, it would be the same line on top of itself, and that's a different name. Those are called coincident lines or coincident lines. But these are parallel lines because they have the same slope and different y-intercepts. So let's try graphing these. We'll graph this one in red. Our y-intercept is -4. Our slope is 3/7, so we're going to go up 3. 1, 2, 3 over 7. We can go down 3 over 7. Draw our line. Call this next line our blue line. Our y-intercept is 5, so we go to 5 on the y-axis. Our slope is -7 over 3, so we're going to go down 7 over 3, down 7 over 3, draw our line, and this looks like it's making a 90-degree angle, and it is. And so we're going to look at our slopes here, and our slopes for our red line was 3/7, and our slope for our blue line is -7/3. So what do we notice about those two slopes? Well, we notice that they look like reciprocals, but one of them's positive and one of them's negative. Right? Reciprocals, the reciprocal of 3/7 is 7/3. Reciprocal of 3/7, its reciprocal is 7/3. We just flip-flop our numerator and our denominator. So what we say is that in order for lines to be perpendicular, their slopes are opposite reciprocals, meaning that we take the reciprocal of 3/7 is 7/3, and we have to change its value as far as positive and negative. So it's the opposite of, it's the reciprocal and the opposite of the reciprocal. So we say that's opposite reciprocals. Opposite reciprocals. So they're opposite reciprocals of each other. So just to practice, if I had a slope of 2/3, its perpendicular line would have a slope of -3/3. halves. If I had a slope of negative 1/4, its opposite reciprocal would be positive 4/1. So parallel lines have the same slope, and perpendicular lines have slopes that are opposite reciprocals of each other. Our homework today is homework 20.